Hi everyone, this is a video about conditional probabilities for my X203 IA application. So actually this discussion will be centered around the Monty Hall problem and how to apply conditional probability to solve this problem. And of course with an important theorem, which is the Bayes theorem or Bayes rule, which is very helpful in this problem. All right. So the Monty Hall problem says you are on a show and there are three doors, A, B, and C. And there is a car behind one of the door with equal chance. And you choose a door. The host will open another door that isn't the winning door and also not the door that you pick. So for example, if you pick door A, if the car is behind door B, then the host will open door C. And if the car is behind door C, because you pick door A, so the host can't open A or C, the host can only open door B. If you pick door A and the car is behind door A, the host can open either door B or C with 50-50 chance. Okay, so this is the setup of the Monty Hall problem. So now the host gives you an option to switch your choice after he opens door B and show you that, oh, the car is not behind door B. The question is, should you switch? Well, intuitively, the probability of A being the winning door is 1/3, and same for door C, because that was what we assumed from the beginning, right? Wrong. The fact that the host opens door B tells you something about the winning door. Okay, it's like how now you have more information to make your decision, which is door B is not a winning door. But it's a little bit unintuitive because why does it have to do with door A and door C if door B is not a winning door? Well, this is why we need conditional probabilities. So before we begin, let's quickly recap the definition of probability. All right. So you have an experiment, a sample space S, which contains all possible outcomes of that experiment, and an event E, which is a subset of S. Then the probability of event E occurring is given by this ratio, which is the size of event space E over the size of sample space. Okay, so it's like taking the ratio among the two, right? Pretty intuitive. Now we have two events, A and B, which are both subset of this sample space S. And now we know that event B happens. This is what we mean by given that B occurs. Okay. Now we know that event B happens. We want to know how likely is it for A to also happen. And this is known as the conditional probability. The condition is that B occurs. And this formula over here, which is the probability of A intersect B over P of B, this is by definition, we don't really have to prove it, but we can look at it like pretty intuitively. So when I say given B occurs, our sample size actually shrink, right? Because we don't care about the events where B doesn't occur anymore, right? And in fact, this string sample space that we are looking at is just like B. And of course, this B is a subset of S. And what about A? Because we want to say, given that B happens, what is the likelihood that A happens, right? But we already said that B happens. So the only way for it to happen together is to have this A intersect B, right? But wait a minute, this is not probability yet. It is just another ratio, okay? It's just like, okay, out of all the event in B, I want something that have B and also A. This is what this ratio means. Let me just slightly modify this a little bit by multiply both numerator and denominator by S. So we have A intercept B over S on top and B over S at the bottom. And by our definition of probability of an event, this is exactly the formula that we have. And this is how we look at this conditional probability intuitively. Okay, just the probability of A intercept B over probability of B. Okay, now, how does the event space of the Monty Hall problem look like? So let's do some notation, introduce some notation. We let O A, O B, and O C be the event where the host opened door A, B, and C respectively after you choose door A. So this is very important because now we are only looking at one specific situation where you open door A and the probability of the host open door A, B, and C, or C, sorry. And we let WA, WB, WC be the events where the winning door are A, B, and C respectively. And with this, it will make our life so much easier, okay? And our event space will now look like this. Okay, it's like a two-dimensional table. One takes care of which door the host open, and the other dimension look at how which door is the winning door. I know it looks something like a multi-variable joint distribution table, but don't worry about it. What it means is, like for example, this box over here, it means like event OA and event WA happens, which is OA intersect WA. And this will be OB intersect WA. And of course, the order doesn't matter. So for this one, you can have OA intersect WB, and also or is the same as WB intersect OA, because set intersection is commutative, right? One thing to note here is that this column, let me just erase everything. The first column over here, we don't really have to care about it, right? Because we know that once you pick door A, it is impossible for the host to open door A. So we don't look at event OA at all. And also, we don't have to look at this diagonal. Okay, I'm just gonna click on it. This diagonal, because the host won't open the door that is a winning door as well. Okay, so we are only looking at this 1, 2, 3, 4 boxes. But like I said, this is OB and WA, which is not exactly what we want, right? We want the conditional probability. We actually want this conditional probability, which is given that the host open door B, what is the probability that door A is a winning door, which is this probability? And also, given that the host open door B, what is the probability that door C is the winning door, which is this probability over here? And if, let's say I call it 1 and 2, if 1 is greater than 2, then we should stick with door A. If 1 is smaller than 2, then we should switch to door C. And if both of them are equal, then we should be just whatever, just indifferent between the two choices. Okay. Now we have a direction. Let's see what we have. Back to the problem and try to label something over here. It says that behind 3 doors with equal chance, that means P of WA is the same as P of WB, is the same as P of WC, which are all 1/3. Okay. And the first line says, given that the winning door is B, the probability of C happening is certain, is very certain, which is 1. Is the host will for sure open door B. Sorry, open door C. And similarly, if the price is behind door B and you choose door A, the host can only open door. I think, okay, I make a mistake here. Okay, yeah. So given that the price is behind door C and you choose door A, the host can only open door B, so this will be 1 as well. And the third line says, given that it is winning door is door A, the probability that the host open door B is the same as the probability that he opens door C, which is 1/2. Okay, so this is what we have so far. Okay, these three actually 1, 2, 3, 4, 5, 6, 7, 7 probabilities. But if you look at it, look at what we have versus what we want, this order of condition of event are swapped, right? And we don't really have this this intersection thingy yet. So we need another rule, just another short formula known as the Bayes theorem. And as you can see, this formula relates like the different order of events in a conditional probability, and it will be very helpful in this problem because essentially we want to convert this to this. Okay, we want to like convert between. We want to find a relationship between the two. Okay, let's quickly prove this theorem over here. So I will start from the right hand side. So by definition, we know that this probability of B given A is probability of B and A over P of A. And just gonna copy this over. And as you can see, we can happily cancel out P of A. And because set intersection is commutative, so we can swap the order over P of B. And again, by definition of conditional probability, this is P of A given B. Okay. So this is how we can easily prove this Bayes theorem. Nice. So now, using Bayes theorem, we can easily find these two, right? Because we have this OB given WA, which is 1/2. We have OB given WC, which is OB given WC is 1. We have P of A, we have P of WC. But we don't have P of OB yet. Okay, but don't worry about it. Look at our sample space again. So P of OB essentially says that we are looking at this column of our sample space. Okay, and this has something to do with independence, which I don't think I have time to go in detail now, but it is essentially saying that P of OB is the sum of this probability and this probability. And how I defined this sample space earlier, this is the same as OB and WA plus, actually you should include this OB and WB as well, but this 0, so I just omit it. And this OB and WC. But wait a minute, you said that, oh, we are still dealing with the intersection thingy which we don't have. The truth is, given all the information that you have here, and with the two formulas, which is one conditional probabilities and Bayes theorem, we can easily translate this into something that we have. And I'm just gonna rearrange the conditional probability formula for a little bit. Where is it? Okay, this. So because we want this intersection thingy as a subject, right? So PA intersect B is nothing but just PA given B times PB. Okay, so we have this. We are trying to convert it in this form, a product of a conditional probability and just P of I believe is WA or WC over here, right? So this will just be P of OB given WA times P of WA plus P of OB and given WC times P of WC. Do we have all this? Yes. P of OB given WA, it's here. OB given WA is 1/2. 1/2. P of WA is 1/3. plus P of OB given WC. OB given WC is 1. P of WC is, again, 1/3. And I believe this is 1/2. So now we have P of OB. Very nice. And I think So now we have all this information that we need. We just need to plug into our formula and compare which one is bigger and which one is smaller. So just gonna quickly compute this. OB given WA is 1/2. WA is 1/3. OB is 1/2. So this and that cancel. This will be 1/3. Okay. OB given WC is 1. WC is 1/3. OB is 1/2. So this will be 2/3. So as you can see, this probability is smaller than that probability, and therefore you should switch to door C if the host open door B after you choose door A. Okay, because this is the condition that door B is open. So to recap, the thing about this Monty Hall problem is that we are doing in a very specific case where you choose door A and the host open door B, but in fact, without loss of generality, we can always swap like the ABC and we'll obtain the same result. And it is always better to switch your choice after the host open the door because the conditional probability is greater. So that's all for conditional probability, and thank you.